Batman was your favorite?
I'm sorry?
Which portrayal of Batman was your favorite?
Christian.
Yeah.
Yeah, I'm on a first name basis.
The one with George Clooney, that was awful.
Val Kilmer was even worse.
Uh,
I just pretend those don't exist. Okay, so we're going to combine some pre-calc stuff with some calculus stuff, and this will be pretty easy. We've done a little bit of this already, and that is looking at limits when you get close to an asymptote. So we have to discuss how do you know if there's an asymptote. We have to discuss how to find that asymptote, and then we need to discuss how to find the limits. And the process is pretty simple. Okay, so left hand and right hand side as you approach an asymptote we're going to be looking at. You need to be able to sketch an asymptote, or at least be able to figure out where you draw the asymptote. And then, most importantly, not get tricked into using an infinite limit when it's just a plug and chug. Okay? So let's start with this. So I took a function, 3 divided by x minus 2. And as you can see from the graph, there is an asymptote. It's a little hard to see because in my infinite wisdom I used green. Sorry. What determines an asymptote in a function? Ah. 0 on the bottom. Is that always the case? Okay.
Yes.
So if I take any function, what makes the denominator equal to 0 will always generate an asymptote?
No, it will generate a hole.
Okay, it could generate a hole. So how do we distinguish between a hole and an asymptote? Lucas?
You can factor it out.
Yeah. If it factors out and cancels, we have a hole. That's not what we're dealing with here. We're dealing with asymptotes. So notice in this function, 3 over x minus 2, there's no canceling there. So sure enough, we have an asymptote. Functions will do one of 4 things around an asymptote. You have a question?
Yeah, will we ever have to deal with like horizontal asymptotes?
Yes, but not for this stuff. That comes later. Monday. Okay. Well, it's later, isn't it? What are we doing? Oh, asymptotes. One of 4 things is going to happen. It goes down on the left, up on the right. It goes up on the left, down on the right. They both go up. They both go down. There's no other possibility. Can't cross a vertical asymptote. Can't ever have a value there. So it just takes that chunk out of the graph. Okay. Looking at the graph, it's easy. Okay, what's the limit as we approach from the right? It goes off into infinity. Notice in this paragraph here, the fancy terms decreases without bound and increases without bound. That means infinity and negative infinity. That's all we're doing today. Find an asymptote, decide what the limit is on the left and on the right. What's the limit at the value? Does not exist because the left doesn't match the right. Okay? So, can we do this without using a graph? We started playing enough with limits to realize that sometimes the easiest way to solve the limit is to draw a picture. Other times, you have no idea what the graph is, so you have to be able to figure it out without a picture. In this case, we're going to look at this function. Now, could you draw a picture of that function? Yes, you probably should be able to, but we're going to do it without drawing a picture and show you the technique for finding the limit. Okay, so let's work in blue today. We want to know, first of all, where's the asymptote? One. Was that a tricky question? Are we all, or is everybody bashful today? We're all bashful. Yeah. Actually, you're overwhelmed by the heat and humidity in the room. Question?
Can we find the asymptote again?
It's whatever makes the denominator 0, assuming there's no canceling to generate a hole. Okay, so for instance, if I have a function, you might say to yourself, I think there's an asymptote at 1, but that would be false. Because it cancels, there's actually a hole at 1. This one, there's no canceling, So therefore, it must be an asymptote at x equals 1. We're good? Beautiful. Now we want to know what is the limit as x approaches 1 from the positive, and what is the limit as x approaches 1 from the negative.
Of that function?
Of f of x.
Oh.
In other words, we know the asymptote. Let's do we'll do the right side first. So as we're coming from the positive direction, we know the graph is either going to do this, or it's going to do this. It's either going to increase without bound, or it's going to decrease without bound. How do we figure out which one? Barring, of course, the obvious of plugging it into your calculator and looking at the picture. Any ideas?
Increase. I say increase.
I don't care what the answer is. I want to know, how do we find the answer? Matt?
Positive or negative?
Good. And how do we figure out if it's positive or negative on the right side? Lucas?
You can put in smaller and smaller x values, see what the trend is.
Good. I'm actually only going to put in one number, because I only need to know one place. Okay. So if I take, let's suppose this is our value of 1 here. Again, I said we do it out without graphing, but I'm going to show you the picture first. I'm coming from the right, so I'm going to pick some point, let's say there, and test it. And I don't even care what the value is. All I care about is, as Matt said, positive or negative. If it's positive, it goes up. If it's negative, it goes down. What would be a smart number to pick over here?
1.
2.
2. Can't do 1. 1 doesn't work. Gotta go.
That's for the, oh,
Yeah. 2 would work nicely. If I plug 2 into this equation, is it positive or negative? It's positive. So therefore, this is
Increasing without bounds.
also known as the sideways 8. Good.
Can we just write that or?
No, that's it. Yeah, you don't have to write increases without pound. That's just showing off, Dan. No showboating. What about 1 from the left? What would be a good number to the left of 1? Negative 2, 0, negative gabillion. Okay, let's put in negative gabillion. What's negative gabillion minus 1? Negative gabillion minus 1, which when you square that, positive, and therefore positive. Easy? Yeah, good. The only thing that causes people problems is I'm amazed at how many times this happens. They have a brain fart and they try to pick a point to the right of 1 and they pick like negative 2. Okay, so number lines hopefully are not going to be an issue, but sometimes it does create an issue. Just for giggles, what's the limit as x approaches 1 of f of x? Does not exist. Correct. But wait a second, they're both infinity.
One's going to left.
Left-hand limit matches right-hand limit, doesn't it? Yeah, so Gracie and I were arguing about this yesterday, and I don't have a solid answer for you, and I know I've mentioned this in the past. The AP gets a little weird with this, and a lot of it depends on how the question is asked. If they say, what's the numerical value of the limit, you would go with does not exist. If it just says what's the limit, you could go with infinity. This will always work in this case. Sometimes you can sneak in infinity there.
Why doesn't it exist if they're going to assume?
Because they hype on the fact that infinity is not a number, it's a concept.
Okay.
So if they're looking for a numerical value, they're looking for a number that's not a number,
Okay.
does not exist. Okay? Let's try another one. Come over here. Okay, so there's a picture. The picture confirms what we thought. They both shoot up to infinity. Lovely. How about that one? Where's the asymptote?
1.
X equals 1, so nothing big changed there. And so we want to know what is the limit as x approaches 1 from the positive of g of x. And we want to know what is the limit as x approaches 1 from the negative of g of x. Similar to the previous problem, what number do you want to use for the first one? 2. If I plug 2 into the equation, am I going to get a positive or a negative answer?
Negative.
Negative. So therefore the limit is
Negative.
negative infinity. How about the bottom one? What's a good number?
Negative.
Negative 2. What do I get for an answer?
1/3.
Yeah. All we care is positive or negative.
Oh.
Okay, we good? It doesn't matter what number you plug in. There's a caveat there. It will matter what number you plug in if you have more than one asymptote, because you know we're going to get to that. We're going to get to functions that have multiple asymptotes. So you have to be sure, like let's say for instance I have a graph that looks like this. You've seen a gabillion of these in pre-calc. If I'm testing this asymptote at 1, I don't want to pick -10 because I'm way over here. I got to be sure to pick something in this range to test it. So try to keep it fairly close. 1 away, 1/10 away, something like that. Because again, we don't care about the value, we care about just positive or negative. Okay? Any problems? All right, let's get some, let's look at some calculus speak here so that we can get the terminology under control. The following slides I'm going to go through quickly. All they are is just what we just did written out. Okay, so yeah, did that, and then we put a small negative, did that, yep, good, that's, we found that, good. Oh, 1.1, yeah, we used 2, but 1.1 works vertical asymptotes, good. This is where I wanted to get to. These are the fancy calculus definitions for what generates a vertical asymptote. We already have a good practical definition. Okay, it's what makes the denominator 0, blah, 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 blah. But this is the fancy stuff. I don't know if you need to write it down. I'm not going to ask you to regurgitate it, but I think it is important that you see the language there. So this defines a vertical asymptote. The theorem says, how do you find the vertical asymptote from a function? And we already know this. Okay. We good with that? Excellent. We are almost done. Where's the vertical asymptote there? -1. No canceling. What makes the denominator 0? -1. That one?
One or negative one.
One or negative one.
1 and -1. Oh no.
Or no, there's no asymptote.
Is it just
Oh.
one?
Cancel.
They're both
No, it doesn't.
I'm so There's a hole.
It's 1.
No.
It's just a.
Ooh, I picked a good example.
Just one.
A or B?
What are you going with, Dan?
Just one.
Just one. Dan's saying just one. Anybody want to back Dan on this one? Other suggestions? Taylor?
1 and -1.
1 and -1. Anybody like that as an answer? Ooh, little bigger crowd. You're losing in the polls, Dan. Any other suggestions?
What Taylor said.
I'm sorry?
What Taylor said.
Right, we covered that one already. Okay. Nothing?
What did Dan say?
Dan said just 1. Taylor says 1 and -1.
I don't know anymore. I thought I knew.
Max is abstaining.
Max is
John, you're also abstaining? Okay, coward.
Isn't there also horizontal asymptote?
I'm sorry, what?
Isn't there also horizontal asymptote?
What, you keep throwing horizontal asymptotes. I mean, you got a thing for horizontal asymptotes?
Yeah.
Okay. You're gonna have to be patient then. All right, let's factor the numerator. How's that factor? It doesn't. Oh, you guys are too smart.
Boom.
Let's factor the what's the bottom denominator?
X plus 1 x minus 1.
Any canceling?
No.
Nope. So therefore, where are the vertical asymptotes?
X.
1 and -1. Way to go, Taylor. Well done.
Yeah, Taylor.
Ooh.
Hey, thanks, Max. Can I have some peanut butter sandwich?
Try it. It's really good.
You know,
The butter and peanut butter.
we wouldn't be having any fun unless I threw some trig in there. Where are the asymptotes for cotangent?
Alright, we got 0 and pi.
0 and pi.
Yep.
Oh, well,
No.
it's.
2 pi, 3 pi.
How do you express the repetition of the aforementioned asymptotes?
Pi plus pi k.
Pi plus pi. Pi plus pi k, or you could just say pi k. So it's 0, pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi. What about tangent?
Negative pi over 2 and pi over 2. So pi over 2 plus pi, 2 pi.
2 pi k?
Pi k.
Pi k. Yeah, not 2 pi k. 2 pi k cotangent, or sorry, cosine and sine. Pi k, tangent, cotangent. What about secant?
0 to 2 pi.
0 to pi. So 2 pi.
2 pi.
And
Yeah, it's 0 to 2 pi, but where are the
2
asymptotes?
pi plus 2 pi k.
That's 2 pi.
Where?
5 over 2 and 3 pi over
Pi over 2 and 3 pi over 2 plus 2 pi k. And then secant? No, we did secant. Cosecant.
Same thing.
Same.
Same thing.
No. No. It's, I got this. Pi over 2, pi k.
Pi k? Not pi plus 2 pi k?
I'll go with that one.
No, no, I'm asking.
I don't.
He's getting in your head, Steve.
I don't like this.
Can't handle the pressure?
No, I'm right.
I understand. Yeah, it's every pi, 0 pi, so you were right the first
Okay.
time. Okay?
Thank
So
you.
what's supposed to happen? 5 plus pi.
I don't know what's right.
0 plus 2 pi k. Okay, so 2 pi k, but it's 0 and pi, 2 plus 2 pi k, so you can write it as pi k. Okay, we're done. I told you, easy, right? Good. So what we're building towards here is using calculus to, we're eventually going to draw really detailed graphs of functions. So you did this in pre-calc already. This is pretty much a pre-calc review, except we threw in the idea of limits. But we're going to use some more calculus stuff so that by the time we're done, we're going to have really accurate graphs of very bizarre functions.